right, we have talked about horizontal projectiles. We're going to expand that idea and talk about things that have been projected at an angle, which means, let's say we have some red level ground like that. We're going to shoot an object up into the air with a velocity of, say, 100 meters per second. It's a number I know how to deal with. It's going to follow this path. It's going to hit. We're going to look at how to find how far it goes. It's delta x. We're going to look at how to find how high it goes. And the time to get to each of these positions as well, obviously. So, how far and how high. Before we do that, though, we're going to look at it in a couple of different ways. If we look at a front view, okay, from a front view, let's say this is our ground, we see the thing go up into the air, slow down and stop and come back down. It's a little bit skewed to the side. We're going to call this our y direction. In this front view, the acceleration is equal to 10 meters per second squared down. Okay. Now, the ball has an initial velocity in this front view. If we go back up here to our triangle, it is the initial velocity in the y direction. The velocity in the y direction, according to that triangle, is going to be 100 meters per second times the sine of our angle. Let's say that's 30 degrees. And it doesn't look like 30. We're going to say it's 30. So the initial velocity in the y direction, 100 sine 30, is 50 meters per second. So our initial velocity is 50 meters per second, and that's up. So we're going to make this negative. Now, what we're seeing here in this front view, okay, is that the problem, as far as the y direction is concerned, is just a free fall problem. The ball is thrown straight up and comes straight back down. Well, I know what to do with the free fall problem. I know how to figure out how high or how long it takes to get back down to the bottom. Which means we can do this. If I want how high, the final velocity is equal to 0. And so v squared equals v0 squared plus 2a delta y. That goes away. Negative v0 squared over 2 times the acceleration gives us our delta y. And looking at it, we have negative 50 squared over 2 times negative 10. And our delta y comes out to be 125 meters. At the same time, if we want how long it takes to get to there, acceleration is still negative 10 meters per second. The initial velocity in the y direction is 50. The initial velocity in the y direction is still 50 meters per second. But if we're going for how far, we start here in the y direction, we end over here. That means my delta y is 0. Y is equal to 0. We're going to find our time by looking at the third equation, v0t plus half at squared. That goes away. So I have negative v0t equals 1/2 at squared. This t goes away. One of those t's go away. So if we solve for it, time is equal to negative 2v0 over a. So our time is negative 2 times 50 divided by negative 10. Our time comes out to be 10 seconds. So it's going to take us 10 seconds to go all the way up and come right back down. Or, really, to do this whole thing, it's going to take 10 seconds. So in the y direction for the entire projectile problem, all we have is what happened with the free fall problem. That's all in the y. In the x direction, It's even better. In the x direction, let's take a top view. So we don't see any y stuff anymore. In the x direction, we start off here and we move straight across. And it turns out let me make this better. We have a constant velocity, meaning that the acceleration of the x is equal to 0, which is what we expect. A really easy proof of this, when you stand outside, given that you have normal balance, you don't fall to the left or to the right. If you were to trip, you'd fall straight down, but you don't have a force pulling you to the left or the right, so you don't have an acceleration in the x direction. Well, neither does a falling object. It just moves with a constant velocity in the x direction. So for x direction stuff, the acceleration is equal to 0, and the initial velocity is equal to, well, the x component of that 100 meters per second. So I have 100 meters per second, 30-degree angle. The x component is going to be 100 times the cosine of 30. So that x comes out to be 86.6 meters per second. The velocity of my x is 86.6 meters per second. Yeah, 86.6 meters per second. So to get our delta x, that's the velocity in the x times the time plus half at squared. Well, that's 0. So our delta x, the distance that we go, is going to be 86.6 meters per second times, guess what? That's our time, 10 seconds. So our delta x is 866 meters. That's how far this thing goes in the x direction. This is a very repeatable, very simple process. The big thing to remember is that we have a constant velocity in the x direction because the acceleration is 0. And the entire time we're in free fall, we're moving with an acceleration of 10 meters per second squared down. Now, we're just going to take a look at some general things that reiterate those 2 points I was just talking about. So let's say this is our object. This is our nice parabolic shape for our object. And let's just say that our initial velocity, we'll call it V0. Now if we look at that, V0 shot at an angle of theta, the initial velocity in the x direction is V0, in this case, cosine theta, and in the y direction, it's going to be V0 sine of theta. That's the x and the y components of that velocity. Now, at every point along the way, we know in the x direction that the acceleration is 0, which means that the velocity in the x never changes. At the very beginning, the velocity in the x direction is still V0 cosine theta. Up here, a couple seconds later, guess what? Velocity in the x direction is still V0 cosine theta. At any point you can imagine, even at the very top, the velocity in the x is equal to V0 times the cosine of theta. All the way through, we have the same x velocity. We should write that down, it's important. The velocity in x for any given problem is always the same. Because the acceleration equals 0, that means the velocity cannot change. Now, in the y direction, our acceleration is 10 meters per second squared down. That's at every single point. The acceleration is 10 meters per second squared down. All the way through. 10 meters per second squared at every given point. So what that means is that the y velocity is constantly changing. Okay, if we were to look at it, I'm going to find a different color real quick. Hopefully everything's not gone. It is. Okay, if we're to look at it, we start off with our initial velocity in the y direction, and we notice that as time goes on, as this thing goes up and up and up and up and up, the velocity in the y changes to where it gets to 0, and then my object begins to accelerate back down more and more and more and more. The y velocity always changes. When we get back to level ground, guess what? It's the same v0 in the y that we always had. v0 sine theta. A couple of things to look at for projectiles.